So we will finish the workshop on the same topic as we started, Orbite Finite, Nominal Monoids, and by Thomas Colcombet from IRIF. Right?
IRIF.
Yes.
Okay. Oh yes, I did not put it. So yes, this is the last talk of this wonderful workshop. So I think everybody will remember this week for many reasons, but one is that this was a wonderful scientific week. And also I take the occasion to thank the organizer of the program, because all these months are very, very productive and very interesting. So those who have the chance to be here have a lot of chance, and I'm part of them. Thank you very much. So this talk is about indeed nominal monoids. So it refers to several talks. We had register automata, we had these atoms, we had these CSPs, and we had this programming this morning. It's also in connection with characterization of logical classes by algebraic means, like in the talk of Howard, also at the beginning of this talk. So what are the two key theorems that we have in regular languages and that we use as a kind of yardstick for understanding things and for knowing what we have in different classes of languages? Well, so that's what I call the fundamental theorem of regular language. Everything is equivalent, almost. So monadic second-order logic, recognizability by monoid, deterministic automata, and everybody knows, like a long, never-ending list of such things. And there is the second part, which is essentially the Schützenberger result and this McNaughton-Papert result, which says that if you furthermore restrict yourself so the monoids to be aperiodic, then the logic to be first order, then you have, you have other models, then against you have perfect equivalence. And for those who work with automata, this is kind of the thing we look at. If we have a new model of things, what do we have among these results? So in plenty of classes. So if you extend the models like to omega words, or even better to words of countable length, you may wonder about having exactly the same kind of equivalences. If you go to trees, you can also try to do that. That works a little less good, but okay. Or cost functions, you can do similar things. And what we do here is try to do this for nominal, for the nominal world. So now we are not talking about, it's still finite words, but now the words have values that belong to some infinite universe of datas or names or integers, whatever you call them. And we want to see if we can recover part of these results. Okay, so what is the story of that? Regular data languages. So this notion of data is the name that is given, I think, in the database community. So the idea is to typically encode identifiers. So imagine you have a word, and this word has a list is a list of things, and for instance there are books, and you want to know where they are. So the basic relation that you want between two pieces of data is only the equality. You will not compare things for any other thing. So that's why you try to model. And it has many applications, so names in programming, in semantic of programming languages. You can do many things with that. So, but for us, we have a set D of datas, or A of atoms, or N of natural numbers, whatever. And we can only compare them toward equality. And when we talk about a word, essentially all the example will be like that. Sometimes we can add a finite part to it, but that's what it is. So how can we design devices for recognizing language of such objects? Well, the first proposal was the one of Kaminsky and Frances, which is you add registers to your automata, and these registers can store these values. You have finitely many of them, and when you advance in the word, you can pick the value, compare with the registers you have, decide to keep it, throw it away, and you go on like that till the end. But when you go in this direction, you suddenly discover that the world is not so nice. Even if this model looks like the simplest you can imagine, then deterministic is not the same as non-deterministic, and even there are several versions of non-deterministic. It's also different of being monoid. It's also different to be alternating. It's different. Well, everything is different. Nothing works. And even worse, if you want to solve the basic questions that usually are decidable for languages, so typically emptiness or universality, then you turn out to be very quickly undecidable. So this is the case if you take a non-deterministic register automata, in this sense that should be register, then universality is not decidable. If you want to decide the satisfiability of first-order logic, I will talk about what are these logic. It is also undecidable. So things do not look to start very well for having a strong result where two things would be equal. Oh yeah, so I missed, there are still nevertheless some things that are decidable, but for classes like the logic first order, we know that it's decidable only when it has two variables. And in any case, what we can conclude is that it cannot, all these decidable cases cannot be understood as notion of regular languages. Because of course, FO2, if you look when there is no data, this does not look like a regular language. It's extremely weak. So can we do better than that? So this is our result, and I will take most of the time to try to explain what's going on there. But so what is important is that it's on the left side, we have a logic, which is a monadic second-order logic plus some rigidity thing. And so if we use it over normal words, this is full monadic logic completely syntactically. So we did not throw away anything from normal logic. And on the right side, we have an algebraic object, which is the one of a nominal orbit finite monoid. And we have this aperiodic version. If you take exactly the same rigid thing and you combine it with first-order logic, then you get the aperiodic fragment of the nominal monoid. So we have something that looks...
So the word aperiodic is missing?
Yeah, so
aperiodic.
Yeah, this is aperiodic. Yeah, sorry. Well, I made copy and paste, so it will be missing a lot of time in this talk. So first question, what are orbit finite nominal monoids? Well, we've seen so many things during this workshop. I think there is no problem, but I will just recap some things. We have this set D of datas that we can only compare toward equality. So I don't know what is that. And we work with these nominal sets. So we have the permutation of these datas that act on all the sets I will be talking about. There is also this very important support assumption that I will not mention here. And typical examples are like the set of datas or the square of the set of datas or words or finite set. And when I say set, I mean that the permutation of the datas do not act on it. It's like a normal set, no datas in it. Then you have this notion of orbit finiteness, which is that there are only finitely many, these are the sets that have only finitely many objects up to permutation. And so typically finite set, or these are, but words are not. And words we care about, of course. And we have the notion of being equivariant, which is like being invariant under this permutation. All this is the same. So now, what do we do with that? Well, we just take the normal definition of a monoid, but we instantiate it in this universe, in the category of nominal set. So we have this set, well, it's A here, but it's like the datas that we use as an alphabet. Then we have a monoid, which is like a normal monoid, but the only thing is that instead of being finite, it's orbit finite, and the product has to be equivariant. And we have a morphisms from the words to this monoid, and this morphism needs also to be equivariant. So all this is insensitive to any particular value. And we have a finite subset of the monoid, which is also equivariant, which is the set of accepting elements. And when we have these pieces of three elements, a monoid, a morphism, and a subset, we can talk about the language of data words, so words over this alphabet recognized by it as in the usual way, those words such that the image by the morphism belong to F.
So is that on the right-hand side, is that little f, should that be an H?
Yes.
Yeah. sorry for that. So here come some examples. So usually the example only talk about the data part of it. So this first example says, oh, my word has its first and last values that appear equal. And so we can do this by a monoid, and this monoid is like, so we have the one, this is the one of the monoid, the value of the empty word, we have no choice about it. And then it's d square. So I'm saying that it has 3 orbits because if we look carefully at it, there is the diagonal which acts as a different orbit, but we don't care about that. And essentially, when we have a word u, we want our morphism to send it to the pair of its first value and last value. Okay, so and we need this should be a morphism of monoid. So of course, if I make the product of a word that starts with a d and ends with an e, with a word that starts with a d prime and ends with an e prime, I don't care about what are e and d prime. I just throw them away, and I'm just saying I get a word that starts with a d and ends with an e prime. So the morphism starts from the letter for all data d, and then by product you get to have this morphism. This is an operator. And then we accept those words that have twice the same data value, meaning the first one and the last one are the same. So we have here other examples. Words such that every consecutive datas are different. So it's the same thing, but now each time so it's the same thing, but now we have a 0, which is the absorbing element of the monoid. And whenever we make the product of 2 words, we carefully check that the data value that is at the meeting point are different. Otherwise, we fall down to the 0 element, says there are 2 consecutive values that are equal, right? And otherwise, it's, well, that should not be that. That should be just d squared. Never mind. Another nice example is the following one. You give me an integer k, non-negative integer k, and you are just verifying that your word contains exactly k distinct data values. And then the nominal monoid is as follows. You have an absorbing element. As soon as you have found more than k values, you just go to this element. And otherwise, you just construct a set of the data values that you have seen in the current word. So in this case, the product is just the union of the sets, but sometimes you exceed k, and then you should fall down to 0, right? And the morphism starts from the letter, and say if you have a letter d, then the only value that you see is a d, and then you accept the sets only of those orbits that have support of size k. Right. And you can make non-example words such that all datas are distinct, for instance. Well, there is a minimal nominal monoid for that, but it has infinitely many orbits. Because essentially, if you want to check in the product of 2 words, if suddenly you make appear some value that repeat twice, you need to know all the values of the first word and all the values of the second word, and that's much too much for an orbit finite thing. Right. So now we know what are these objects. Yes. Now what are the logics for data words? And here again, I did not, it's very well specified in the literature. So here I'm making I have this finite part B, which is A, B, or an alphabet, a finite alphabet, and we have this data value. So a word looks like that. And I'm defining first order logic with this tilde operation, which is normal first order logic where variable with range over the positions in this word. We have like all the standard things of first order, but the new predicates that we have is x is equivalent to y, and that means the value at position x and the value at position y are the same, right? So this gives you a logic, and if you give it a word like that, it either accepts it or rejects it. And the monadic second order version of it is exactly the same. You take this logic and you add monadic second order quantifiers and variables to it. So for instance, the first and last datas are the same in my word. Well, very easy. I say let for all x and y such that x looks like the first element and y looks like the last element, x is equivalent to y for this thing here. Some data reappears. Okay, there is x different from y such that x is equivalent to y. Some data appears an odd number of times, then you would use some monadic second order quantifiers to do that. So just one thing you have to remark in this definition is that because you never talk explicitly about a data value, you can only talk about what it is to carry the same data. You are invariant under the permutation. If you apply a permutation of the name and you apply it to every letter, if a formula holds before, it also holds after. So the objects that you construct are always equivariant. So I mentioned undecidability. In fact, it goes very quickly, but it's interesting to see it because...
Tell us what rigidity is, though?
Yes, I will tell you what rigidity is. Well, I just have 10 minutes left. Maybe not. No, okay. I will. So why is it undecidable? It goes very, very easily. Let's take this alphabet. You have a finite part with two letters A and B and an infinite part, and then we will interpret graphs in it. So a vertex will be for me a maximal interval of positions that all carry the same label A. And I put an edge between two vertices if they contain one position that have the same value. So for instance, here I have a word. I've put in bold those that are the maximal intervals of A's. And having same value defines this. So I can see it as being interpreted in this triangle. And it's obvious that like that you would construct every graph. And since first order is not decidable on the class of all finite graphs, it's undecidable. So then what do you do for that? So there is a long story of things. So you can say, oh, but then I will make a logic that looks on graph like something that is decidable, like a modal logic or mu calculus logic. There are some versions of that are called walking logic. But that's not what I want to do. Here my goal is to capture the expressive power of orbit finite nominal monoids. So for this, I require a very specific notion, which is rigidity. Just before, to tell what we know, this business of nominal orbit finite monoids was introduced by Mikołaj Bojańczyk in 2010 under the name of data monoid, because he reconstructed everything from scratch. And what we know is like that. Every data language that is recognized by an orbit finite monoid is definable in this logic. If you are definable in the first order fragment, then you are aperiodic. I will not talk about what it is. And that's the most difficult part. If you are recognizable by an orbit finite aperiodic monoid, then you are first order definable. So that looks like that. You have things that are orbit finite monoid, and you can intersect them with aperiodicity. And what you know here is that this part is exactly the one that is first order definable into this part. It's a bit weird. Well, it's a very interesting result, but it sounds like it's not finished yet. So that's what we do. Here I should give you examples of people that live in every of these classes. I don't know if I'm doing it. Well, you can ask a question if you're interested. So what we have here, in fact, is that for these two classes, we have an exact syntactic logical equivalent for defining these languages. So what is rigidity? Rigidity is so it's a way to guard this equivalence test. So if we allow to compare any value x or y and say, do you carry the same data value, you immediately run into trouble because you define things that go in every direction and every graph is definable and nothing is decidable anymore. So you want to restrict it, and the way you restrict it is by using rigid guards. So imagine you have a formula phi of x, y. No other free variables. I mean, I will tell it after, but I can tell it right now. Then you say that it is rigid if you see it as defining a relation on the position of the word, then this relation is a partial bijection. So it's a one-to-one partial map. If you know x, there is only one y for which phi can hold. And if you know y, there is only one x for which it can hold. So you assume that it is the case on every model. You can say, so, examples. The first, x is the first and y is the last. That's a bit trivial example, but indeed it happens. If you know x, you know y, and well, you don't even need to know x to know y. But the successor relation is of this form, because if you know x, you know who's the successor, and if you know the successor, you know who's the predecessor. This one is a bit more, it says x is on a position labeled by an A. Y is also on a position labeled by an A, and they are on this order. And in the interval, there is no other A's. So it's like, it's a relation that says I'm on an A, I jump to the next A, and I can go backward in a unique way. So it's also a rigid thing. Right. So one complaint that is done sometime about this work is that it's a semantic notion. So it turns out that we can decide it in the process, but in fact we can also enforce it syntactically. And how do we do that? Imagine you have a formula phi of xy. Okay, someone tells you it's rigid, but you have no idea whether it's rigid or not. Then you can construct a formula phi prime of xy that says phi, okay? And furthermore, it says if you take any other x prime that is in relation with y, then x prime should be equal to x. And same same for y. What does this formula? It does something, it recognizes a subset of the graph of the relation defined by phi. And if phi happens to be rigid, then it's exactly the same set. So it's a way to enforce syntactically to be rigid. Yes? Yes, so the phi prime is always rigid, that's the point. Right. So what is rigid first order? So you remember this testing that two positions carry the same data value. Well, you only allow it if it is guarded by a phi that is rigid and should not contain any other values, right? So that's the definition. So, I mean, this looks good for existential quantifier, like there exist x and y that are guarded such that they are equivalent. But if you want to do it with universal quantifier, you'd like to have something, if x and y are equivalent, then x is equivalent to y for all x, yes. But in fact, this is just syntactic sugar because phi of xy implies x is equivalent to y. You just take this previous construction and you add disjunct with the negation of phi. So this means you have the two cases, yes? So now in this logic, we can pick our example. The first and last value exist. That's because there exists x, y, such that, and then x is equivalent to y, but you guard it by first of x and last of y, which is rigid. So it's a valid thing. Every odd position letters carries the same value. Well, you define in monadic second order logic what is an odd position. And you can define what it is to jump on the next odd position. And then you say every two odd position has the same value as the next one. And then you have explicitly, rigidly linked one value at an odd position with the two next one. There are two consecutive letters that carry the same value. You can also do it just by saying there exist x and y such that are related by successor and can share the same value. But you see that if you want to do something like some value appears twice, that was so easy. There exists x different from y, and x is equivalent to y. Then it's impossible to guard it because you have no clue what is the relation that would allow you to jump from x to y. Okay, so the proof goes in two directions. What do I want to say exactly in the 2 minutes that remain? Okay, this story is about saying if you want to transform monadic second order logic into monoid, then either you use type if you are of the compositional family, or you use a closure operation if you are more used to languages, but essentially that's exactly the same in this context. And so essentially you say if I have my regular languages have many closure operation, then I will have one that would correspond to each of the construction of my logic, so I can compile my logic into operation on regular languages. And, but the problem is that the existential quantifier means a projection, so it's a power set. And in general, if you take the power set of an orbit finite set, then suddenly it's not orbit finite anymore. So power set is not allowed. And so here there is, the solution is to make to be careful about how we make this projection. And we have this property of projectability. And this essentially this says that whenever you want to project at some point to remove piece of the information, so which is a projection, if you reach the same orbit, then you have to be equal. And it happens that if you have this property, then the power set, it's infinite, but the elements that you really need, they are orbit finite. And in fact, you can preserve this property. So you can compile with the standard algorithm your logic, and you just maintain the information that everything is projectable. So that's one way. And the other way, how much time do I have?
Can take 2 minutes.
2 minutes, yes. So for the other way, I just want to show you that it's more complicated than the usual one.
3 minutes.
4. So usually when you have a monoid and you want to make it a formula of MSO, what do? You say, that's very easy. My monoid, I can even see it as a deterministic automaton. I use an existential quantifier, I guess the run, and then I check that everything's consistent, done, right? Here that will not work at all like that. And I will try to convince you on an example. You remember this example? That's not the one I wanted. This example that says k value appears. Exactly, not this one, yes? I will show you how you construct it, and you will see that you need to nest guards inside guards inside guards k times, which essentially rules out any of this simple construction where you would guess everything at the beginning and make local check. And so you want to have k values. So the first thing you say is value 1 xy, and value 1 xy is a formula that tells you in the interval from x to y there is exactly one data value. So x has to be smaller than y, and whenever I jump to the successor, it needs always be the same data value. And now, when I do that, I can define an operation successor 1. This one would be in some sense successor 0. And it says something like that. X is before y. If I look at things that are in the interval without the endpoints, then it has only one value. But if I look from here to here, it has 2 values. And if I look from here to here, it has 2 values. So in some sense, it's a rigid way to jump to the next point, leaving in the interval something that has only one data value, right? And this is something which is rigid. And now you can define to have what it is to have 2 values. Well, you do in fact exactly the same thing, but you jump by longer steps. So you can to define 2 values, you need first to define 1 value and use it in a guard and so on. So that's that. Well, you go on, you do the language, and that shows that that essentially, I mean, you cannot do as for normal languages. The question is, where does this induction come from? Like this value 1, because at some point you have a monoid and you need to construct this formula, so you need this induction come from? Well, it comes from the Green's relation of the nominal monoid. So just this to say that a good part of this work is to make a very precise analysis of how do look the Green's relations in an orbit finite nominal monoid. That's like the internal machinery for understanding how to produce the formulae. And then there is a conclusion that says exactly all what I said, because I'm late. And it has a funny application, which is that if you have an orbit finite monoid, you can see it as essentially a letter that represents the orbit, and then tuples of variables, and with possibly permutation among these variables. So typically, for instance, you can see the set of pairs of 2 distinct elements. you can see it as this, an ordered set of an ordered pair with a group action saying like X and Y are the same thing. Like switching X and Y is the same thing. And one consequence of this construction is this fact that if you have a finite monoid, you can always see it as the quotient of a monoid that has no permutation like that. And which is not an obvious result. And we don't know any other proof of it, but the way we do it is that we construct a kind of language, we construct the formula, we go back to the monoid, and this permutation stuff has disappeared. So that's how it works. Well, so I think I conclude now this talk. And well, again, thank you, everyone.
Hearing none, I'd like to thank the organizers, Neil and Anus and Alexander in absentia, and the staff of the Institute, and all of you for being here. If you stay around, tomorrow the Institute is closed, a holiday, it's Veterans Day, and safe travels if you travel soon. Okay. Thank you.